Back homework set 17, we're working on the last problem, 5.4-6, and we're just going to jump in. Okay, this is a fun problem. So here they're talking about you have a deflection at the midpoint. They tell you what the deflection is. That's what they got right there. And in part A, they ask, what is the maximum normal strain at the top and bottom of the bar? Okay, so in the solutions, they give us this wonderful equation and then expect us to pretty much go from here and then link it back to our strain equation, which is this. The problem with using that equation is it's very tricky to actually solve for rho, and usually the recommendation is just using Desmos or Wolfram alpha in order to get rho and then to be able to plug it into this equation. There is another way of doing this using more geometry stuff. So if we have our problem set up like this, and then we just look at one section, right? Because our whole goal here is to find rho. Once we find rho, it's very straightforward, right? You just plug into that strain equation. But so if we look at this problem, we have over 2, we have rho, and then this length right here. So we know basically we would have something like this, right? And we'd have our deflection right here. And we know that from this point up to this point is our radius. So if we want to know what this distance is, all it is our radius rho minus that deflection. All right, so now we have a triangle, and from there, all you're doing is just your classic triangle fun, I guess you could say. And you can just start plugging things in. So you have using that. So a squared plus b squared is equal to c squared. That's basically that equation. And then you just start expanding things out and you just start simplifying, right? So if we expand this guy out, let's see, we're going to get rho squared. So I'm expanding this guy, rho squared minus 2 rho sigma plus squared plus L squared over 4 is equal to rho. It's a bit squished, but hopefully that's clear for you guys. That's squared. Okay, so we can see that these cancel out, which is really good, because then the only thing we have left is the negative 2 rho sigma, and we can actually bring that over to one side, and then we'll have sigma squared plus L squared over 4, right? And then you can see pretty straightforward. Then you have your rho function, this plus L over 4 squared, this whole thing. I'm just bringing 2 and sigma, right? You go from there, pretty straightforward setup. So then you find, you get your rho value. And then from there, you just plug it into your strain, negative y, which we talked about in the last problem. You can kind of interchange those because they're not really specifying at which point over rho. So then, bam, be able to solve for the strain, and that's how you do part A. So you can do either way. Obviously, this way you get a little bit more understanding as opposed to using the way the book shows, using Wolfram alphas really been the only way I've seen how to do that. Okay, so now just create the new slide. Part B, they're asking for if you're given this allowable strain and the deflection cannot exceed this amount, so they've constricted this guy right there. What is the maximum permissible length of the bar? So now we're trying to solve for L here, right? So if we kind of work backwards a little bit, it's a lot easier this way. So you have strain Y over rho, right? And we just kind of work backwards to solve for rho because we have 0.06 is equal to, we know what the thickness is. So then that's just our 0.4 divided by 2 over rho, right? You can get rho ends up being 0.66. Okay. So then you have that set up, and now we go back to that original equation with the deflection. It's a lot easier solving it this way instead of trying to solve for rho using this equation. Over 2. Okay. So now we have this. I think I forgot to mention in part A, but this is theta. In the original equation in the book, I believe, but then using just the approximation method, because it's such a small angle, because like in this picture the deflection looks pretty big along here. It looks like it's very bent, but in reality it's a very, very small deflection. I mean, in here you have a very long bar, but it's only 4.3 millimeters. So that's why they use the approximation. That's why the equation is set up like that. But continuing, so now you have this, and you're solving, I guess in this equation, we are going to keep it, L over 2p, but we're just going to leave it like that for now. So then if we simplify this out, we have L over 2p is equal to cosine of 1 minus this. And sorry guys, I just sorting this out in my head really fast. Let's try that again. Let's see. So you have deflection over rho is equal to the 1 minus cosine. I'm just going to keep it on theta because it's easier to write. Simplify that out. So then we have deflection rho is minus is equal to cosine theta. Right, and then from there we just get theta is equal to cosine inverse of 1 minus over rho. Okay, and then obviously that is equal to our L over 2p is equal to the cosine 1 minus rho. And then we're able to solve for L because you just bring that over and it's 2p. And you get your L, which is 2.003 meters.